Good morning, mathematicians. Oh, I forgot to pull my YouTube up ahead of time. Oh, man. What a tragedy. Good morning, mathematicians. Oh, that's not what I wanted to do. What did I want to do? Oh, man. Open up chat. What a tragedy. That's what it was. And get back to our reading through research papers. Well, one research paper in particular. So let's dive right in. Let's review the Langlands correspondence. We're all familiar with that, right, gang? We'll review their notation. So, we've got our quasi-split group. We've got our peer inner forms. And our peer packets are going to be just the unions of all the collections of irreducible representations. Yeah, we got this Kotwis isomorphism, very helpful thing. Technical result about Langlands parameters. By local Langlands correspondence, we mean a collection of maps such that compatible with Langlands classification. For any irreducible representation, we have this. Yeah. Okie dokie. Everyone happy? And now the Kasdan-Lustig hypothesis. Yay! We all love the Kasdan-Lustig hypothesis. In order to prove this conjecture, we need to assume it. Hell yeah, we all love the PKLH, which says, well, we've talked about it a lot on this channel in the past. Maybe there's lots of new people here, but we've got these varieties which have a group acting on them, breaking it into finitely many orbits, and those orbits should be in bijection with the Langlands parameters of infinitesimal parameter lambda. And then what do we have? Well, we've got local systems on each of these orbits. So I guess these mu things, sometimes we call them standard sheaves, although that's dangerous terminology. My group calls them standard sheaves, but that's also could be dangerous terminology because they shouldn't be confused with standard perverse sheaves. Speaking of perverse sheaves, we also get a simple perverse sheaf. Well, here it's framed as attached to every enhanced Langlands parameter, so we can also view this as one attached to every orbit and its local system. And, well, we have this relationship between these things in the Grothendieck group. So, in other words, we get these, we can, if we re-expand it this way, we call these coefficients m sub g. So these are just the multiplicities, expanding these in the Grothendieck group. And yeah, the punchline, the takeaway is that the Kasdan-Lustig hypothesis says that this should be true. So more or less, it says that these two matrices are transpose of each other. No one has said hi yet in chat? Is anyone Someone say hi if you're there. It always freaks me out that maybe chat isn't working. It says 9 watching. Maybe let me restart chat here. Hi, hello. Okay. Glad to have you here. Glad to see chat is working. Wait. Oh no. Did stream freeze? Hopefully it didn't freeze for other people. It looks frozen over here. Oh, that's because I hit pause. Never heard of desideratum? Oh. Yeah. It is not an uncommon term necessarily. It is yeah, sometimes it will be in a book or a paper, as in to say these are like the contents of it. Sometimes it'll say that, but also yes, this is in Langlands. Well, I should say in Langlands, it's not uncommon terminology to say the desideratum of the Langlands correspondence, to just mean the list of defining conditions, basically. The data. Defining it. Okay, so now we've made it through the background. It's time to get to the juicy stuff, the FPP conjecture, which I don't know who was joining me yesterday, but yesterday we did verify it for ourselves in some cases. I gave you guys homework. I hope you did your homework. I hope you verified it in the other cases. Oh, the thing desired. Oh, is that what it translates to? Huh. Thanks for letting us know. That makes sense. Who among us does not desire the Kasdan-Lustig hypothesis or the Langlands correspondence? Okay. So here's the theorem. Suppose G is a pure rational form, and assume there exists a local Langlands correspondence for G, satisfying also the Kasdan-Lustig hypothesis, and suppose that pi is an irreducible unitary G representation with Langlands parameter phi, then the exponent of the infinitesimal parameter satisfies this for every simple coroot. Right on. Let's find out why this is true. The Levy subgroup M at most 1. So if lambda is the equivalence class of infinitesimal character for LG, then in this subsection we associate a Levy subgroup to it. This Levy subgroup will play an important role in theorem 3.1. Recall that the standard parabolic subgroups of LG is in natural bijection with the gamma stable subsets of the roots of the dual group. Every standard parabolic subgroup is a semi-direct product as such, where P hat is a standard parabolic group of G hat. There's a unique Levy factor containing M naught. What is M naught? M naught. Maybe a small typo? We'll just pretend it's a small typo and we'll keep going. And this subgroup is preserved by the action, and we write this. Standard Levy subgroup is anything arising in this way. We now regard lambda as an L parameter for LG, trivial on SL2, and we write this. So we should be able to factor it in this form, where this is the tempered piece. So, okay, I'm gonna need to write this down. Whoop. Let's see if I try stacking things this way. It's kind of weird. But bear with me, gang. Oh, that doesn't really give us a ton of space, does it? Oh, it'll work. Okay. It'll work. I do still wish there was ways to get rid of all of these things. I don't want these bookmarks to go away, but life would be easier without them. Okay. So what's the recipe here? The recipe is we take... Oh, we need to plug in. So the recipe is we take this parabolic, there should be some tempered factors through a levy, and new lambda, some corresponding exponent, and then L, m at most 1 of lambda is going to be the standard parabolic, or the standard levy, which is given by the roots of this levy union the roots of G that are not roots of the levy, but for which this condition is satisfied. Okay, we should probably try and work out some examples. Clearly, this only depends on these two things, and in fact, only on nu, since L m lambda is the LG centralizer of this thing by proposition 2.3. Okay. So let's try to work through an example, possibly. So let's go back to here. Like, I wonder, in our GL2, if we think about, maybe we should look at GL3, because it's slightly more, there's more going on in GL3. Right? If we look at GL3, then well, I guess maybe one thing I should do is understand how these Langlands triples arise. So maybe if we look at well, let's start with GL2. So we have we got this guy, and we got this guy, and the Langlands parameter for this should correspond to, so this will be like, so lambda is nu 1/2, nu minus 1/2, and then this will be determined by the pair where it's this and this upper triangular matrix, and then this one just goes to lambda. Yeah. So I guess we could use the Langlands correspondence to get right. So let's see, our desiderata for the Langlands correspondence says, what does it say? Right. So if I take that triple, oh, it's the same nu. It's the same nu in both positions. So that should give me the nu. Interesting. So, let me pull this up. What are our Langlands triples here? Well, this one is G. I mean, this representation itself is tau. This is the Steinberg representation, by the way. And there's no twist, so it's just 0. That's its Langlands data. And the Langlands data of this one is the Borel and the trivial representation, and then 1/2 minus 1/2 is the exponents here. What was I trying to figure out? Gang, it's so quiet today. Chat is so quiet. The usual noisy boys aren't here. I bet it's because everyone's just working so hard at doing the homework I gave you from last time. People who use Latin words in math give you the ick. Well, you're gonna have a hard time. In math. Good morning, Boris. Good morning, Tenacity. Gotta get that coffee ASMR going. I don't know how often my mom tunes into these live streams, or how long she listens for when she does, but I'm gonna try again to say hi, Mom, because she didn't message me yesterday, so she didn't hear me saying hi last time. Where was I here? Oh yeah, I think because we were trying to sort this out. So I wanted to write, I wanted to figure out what the Levy group would be for this one. You just realized your name rhymes with Taurus. Actually, so I don't remember who I first heard this convention from, but I've heard the convention of actually calling something in math a Boris, because we often make a choice of Borel and a torus contained in that Borel. And so I've heard that choice of pair referred to as a Boris. So your name actually rhymes with Boris as well, which is a thing in math. Um, okay, I guess what I wanted to do was compute some examples of this, but I'm wondering, um, I'm wondering because the FPP conjecture says that this basically happens when there's a unitary representation. Oh, I guess it doesn't say it can't happen otherwise. I'm guessing it doesn't say it can't happen otherwise, but yeah. So hang on. If the FPP conjecture holds, then if the representation, if you have a unitary representation in here, then the conjecture should basically say that this parabolic is the entire group, right? That enters your top 10 list of things that you say hell yeah. Oh, that make you say hell yeah. Hell yeah. So okay, right? That has to, what I just said has to be true though, right? Because if FPP holds, then if lambda has a uni rep in here, this has to be true, and then therefore this has to be true for every co-root, and so this would just be all of the roots, and so then this would just be G. This group would just be G, right? Surely that's the case. Right? Yeah. So let's check it for this one. So for this one, it would, the group. Wait a second. Hang on. Could I help you to understand what a unique factorization domain is? Yeah. It just says a unique factorization domain is just a integral domain. So a ring with no zero divisors, such that every element has a unique factorization into primes up to reordering and unit. So, for example, the integers, right? Every, what are the units of the integers? Well, those are things with multiplicative inverse, plus and minus 1. And the primes in the integers are the primes. And the fundamental theorem of arithmetic says that every number can be uniquely factored. So maybe this is uniquely factored into some product of primes. And by unique, this just means up to some reordering of the primes, and you might possibly have to multiply by a unit. So you might have to multiply by plus or minus 1. A UFD is just a domain in which you have unique factors. Yeah. Plane Man is back. Welcome back. Lockheed SR-71 Blackbird. Happy to have you on board here. So actually, now I'm a little confused because, wait, let's go back. Let's look here for a second. Right. So this is, we take this triple that should correspond to this. So then I think in the unramified case, this should always be our Borel. If I'm not mistaken, in the unramified case, that should always be our Borel, because if we look at the representation associated to, if we look at the representation associated to By the way, what's another example of a unique factorization domain? I hope I'm not about to say something wrong. I think it's the integers adjoin the square root of 2. Wait, the integers adjoin I. Let me say that. That's a safe one. The integers adjoin I. This is a UFD. This is a UFD. But now we have a different set of primes. So what are the units? You have to be careful, because what are the units? The units, we get more units, plus or minus 1, plus or minus I. And what are the primes? Oh, sorry, this should be units of Z adjoin I. And the primes of Z adjoin I are now, we have some of the old primes, but now we have some of them disappear and split up into different pairs. Right. You watch more math. You don't understand until you got to go for dinner in a bit. Well, what better way to build your appetite than to see some tasty math? So again, I claim that every Gaussian integer, as this is called, so a and b are integers. Every Gaussian integer, again, can be factored uniquely. Into primes up to reordering and a unit. So now times some unit. So for example, 6, we would normally factor it as 2 and 3, but 2 is no longer a prime. But we can write it as, this is 1 plus I, 1 minus I times 3. But that's not the only way. We can also multiply this by a unit, right? So we could multiply it. Yeah, I forget. There's some other way to rewrite it that doesn't look like this. I think you multiply in an I or something. Your textbook did not prove that the number of bases A, where n is a strong pseudo-prime number, is at most that. If n is odd and not a prime, do I know a proof for it? Not off the top of my head, no. No, I don't even remember what a pseudo-prime is. Something that satisfies Fermat's little theorem? Let H be a subgroup of G and the index be 2. Prove that if AB is not in H. Okay. Index of H and G is 2. AB are not in H. Then AB is in H. Well, what have you tried so far, Tenacity? The only way you can ever remember the definition of Noetherian rings is that Z is Nethi, but not RT. Yeah. How could you forget Noetherian? Well, I guess you don't, because you remember that fact about Z. You could do that by choosing representatives for the cosets and then compute the product and see what the coset must lie in. Possibly Lockheed. However, the problem with that is if H is not normal, the product is not well defined. So, gotta be careful about that. If H is not normal. If H is not normal, then yeah, life could be harder. But it's maybe worth trying the normal case first. Yeah, maybe worth trying the normal case first. G is the union of G and GH. Okay. So G is the union of H and GH. Can you assume that the theorem says index to normal subgroup is normal exists? Oh, right. We do have that theorem, right? Isn't that... Yeah, there's all these index 2 theorems, like index 2 and something... Right, index 2 always is normal. That's true. So then actually that makes it easy. I think. Right, so, well, let's see. Tenacity, let's go ahead with what tenacity is saying here for a second. A is this. B is some other thing like this. And then you don't know where to go from there. Yeah, so actually, as Lockheed said, though, I think we have a theorem that says index 2 implies normality. I think that's the trick. And then you can use multiplication in the quotient group. I think that's the trick. You're curious as to what goes on in the mind of someone who is good. Well, you've come to the wrong place. When you took abstract algebra, it's quite difficult for you to visualize a lot of these concepts. Do I picture math problems in my head, or do I solve them completely abstractly? I don't know. I mean, what does it mean to picture... What does it mean to picture something in your head? Like both, I guess? Yeah, and what does it mean to solve something abstractly? I don't know. I don't know. What does it mean to solve something abstractly? I see things in my head sometimes when I'm working on math problems. But also certain things are just solved completely abstractly, or like certain things are just like a formal computation, you know? Visualizing the groups. I don't know. Maybe usually not. Maybe usually not. Abstractly is in pure logic without visualization. Yeah, I mean, I guess it depends. It depends on the problem. Like if I'm solving an abstract algebra problem about groups, yeah, I guess it depends on the problem. Because some things are just formal computations, and like I'm just trying to prove some relation, then I'm just trying random crap, you know. And there it is, just like a very formal computation. But like sometimes I might be thinking about like H as some bubble, and yeah, I'm trying to make it normal, and I'm imagining some like element like firing into it or something, maybe. So like maybe sometimes I'm thinking about that. You refuse to believe anyone remembers the Impl-FN theorem? Oh, implicit function theorem and inverse function theorem. Yeah, but how often do you need it, Boris? I'm sure you'd remember it if you needed it more. Can I help you understand the fundamental theorem of homomorphisms? What is that? What is it? I forget. We've learned about homomorphisms, but this is proof in equivalence in relation to equivalence relations. No, I mean I don't even know what that is. Fundamental theorem of homomorphisms. Whoa, wait, where did my other... Did I close Chrome? Oh, man. Wait, what happened to the paper I was reading? Fundamental theorem of homomorphisms. Oh, do you just mean the first isomorphism theorem? Is that what this is? No, this is something different. Yeah, this is just the first isomorphism theorem. Okay. Can I help you? Maybe. We have not learned about homomorphisms. Well, then I can't help. I mean, the first thing you need to do is go learn about homomorphisms. I mean, you can't solve this problem unless you know what a homomorphism is. So I can't help you until you've learned about homomorphisms. But this was a proof in relation to equivalence relations. I mean, definitely this has equivalence. This is about equivalence relations, but, well, question number one is, do you know what the quotient group is? Do you know how to take a quotient of a group by a normal subgroup? That's the first most fundamental thing. Range Rover, read your paper. Wait, which paper is your? Did you email me your paper? Picturing generic points of spec R and possible challenge. I don't know. You could imagine like a thin film spread out over the entire plane. I don't know. How much do I think that computational skill is obtained by grinding as opposed to innate ability? I don't know how much of it is innate, but maybe just learned at a very young age. I have no idea. I'm sure there's research on this. I have no idea. Certainly anyone can get better at computation, but most mathematicians don't care that much about computation. I mean, it's very impressive and everything, but 100 years ago it was maybe more important. Even then, we were doing, you didn't really need it for proofs, but like, we didn't have computers, and you would encounter large numbers, so. Yeah, exactly, Boris. Very easy to visualize spec R that way. Lockheed, do you assume the fundamental theorem of homomorphisms means yes? First isomorphism theorem, yeah. Pure logic type things could be diagram tracing. Yeah, so those are still visual. Good morning, Matthew. Without assuming the result of index 2 subgroups being normal, A inverse is not in H. Why wouldn't A inverse not be in H, Eric? Yeah, that's not clear to me. It would be like if the A that you happen to choose was in H, then because H is a subgroup, A inverse would have to be in there. And your proof should definitely apply to the case when wait, what was the statement of the theorem? Oh, right. A and B are not in H. Right, sorry. You're right. A inverse would not be in H. Sorry, my bad. And since H is index 2, the cosets of these are equal. Very nice. Very nice proof, Eric. Very nice proof. Very nice. That's a good one. By computational, he meant what I said earlier, learning context, solving problems without relying on visualization. Yeah. Yeah, I mean, just totally depends on the problem, I guess. Diagram tracing is visual, but what you meant, the proof is more a machinery of intuition. Yeah. 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 Okay, I gotta go soon, though. School's offering separate courses in abstract algebra and ring theory. Huh? Ring theory should be part of abstract algebra. But I don't know. Maybe their abstract algebra is a whole bunch of general stuff. I don't know. Do you recommend you just take abstract algebra because it already teaches ring theory? Yeah, I guess so. I don't know. What depends what's I feel like to make that call I would need to see the syllabus for both courses. I'd need to know what you already know, and I'd need to know what you want to know, or what you want to do. So without that information, then I would just say yes. I would say yes, take abstract algebra. But to give you an honest opinion, you're bad at real math, as in anything that requires proofs. Well, I'm glad you know what real math is, and that makes you sad. Well, you could always get better. You can always get better. Yeah. So at least there's that. But also, I don't know, if you're good at computation, there's room for computational mathematics in this world. Maybe the ring theory course is more commutative algebra. Could be, yeah. Okay, let's finish off with a little more from this paper, just so I can feel like I put more of a dent in it today. So we will also take this twist. We may write this, and we also define lambda 1 to be the twisting of the tempered part and inclusion. Recall from 2.3, yeah, this is this twist. Where dw denotes the order of w. What you did to try and get better at real math is force yourself into the details, partly because you enjoyed it. I mean, that's a key thing. You have to like the suffering, otherwise you'll never get good. You can surely get better with more practice, yeah. Okay, so if we regard the exponent being in the dual Lie algebra as an element of the Lie algebra of the center. Oh wait, it's this weird thing with the sub h. I forgot what that was. But also we view that sitting inside G dual, and we take this parabolic decomposition, the standard parabolic associated to it, and we let this be this. And theorem 3.2 implies that the eigenvalues of this are all greater than 1. Theorem 3.2. Wait, where's theorem 3.2? Oh, just equation 3.2. I see. Okay. You try, but a lot of things don't stick in your head correctly. Remembering some definitions or understanding how they work enough to naturally recall them when trying to prove something. Yeah. I mean, just a stupid amount of practice. More practice. That's always the answer. That is natural. Came back to those concepts multiple times. Yeah. Yeah, Jake Cummings has a YouTube channel now, by the way. and he's going through his books. I just saw a video. He's going through his books on his channel. Yeah, the abstractions never end. The abstractions never end. Okay, proposition 3.3. We've got an infinitesimal character. And we've got this Levy subgroup. Then, then the injections between these things are isomorphisms. Oh. Interesting. Huh. Okay, then V lambda sub 1, though. I see. So in the unramified case, does this just give us back lambda? Maybe I need to crunch some more examples here. This is what you tell anyone learning topology for the first time. Actually, you own the Cummings proof and the real analysis book. Nice. Yeah. Who went into topology before analysis? I don't know. There's a certain logic to that. I feel like you could justify either direction. For homomorphism here, we let this be the one cocycle defined by this. Take this correspondence, and we can choose this to lie in here. Writing Z as a shorthand for the exponent for any Levy subgroup, and S in R, we define these. Okay, I'm definitely going to need to compute through some examples. But, I don't know. How do we read a paper? I read every paper differently. Sometimes you read through the general ideas first and then go back and compute, or you do it all at once. Okay, so what's happening here? We define this thing. And we get these two groups. Okay, so one of them should be M at most 1. The other one should be G. And we claim these equalities. Okay. Okay, we're gonna have to come back to this tomorrow. There's a lot going on here. I need to use my brain for other things. Yeah. Okay. We'll come back to this paper tomorrow. We'll continue going through to understand it. Exercises always help a lot. Yeah. I mean, that's all there is to it at the end of the day, is just doing lots of exercises. That's really it. That's all there is to it. So, I will see all of you tomorrow if you're joining me. Been quite some time. Yes, Fimnal, but you came in right at the end. That's too bad. But I'm glad that you popped by to say hi anyways. Anywho, I forgot to turn top chat to live chat, so maybe I missed a bunch of stuff. I don't know. Well, that's too bad. Okay, I will see you guys and QED.